Claro.
Maybe you could do it.
Okay, everyone. So it's 7 o'clock. We're gonna get started. So before we get started, oh, by the way, my name is Meish, and I'm a research data scientist at Axial Healthcare. Today we're really happy to have a lot of first timers. So could all of our first timers raise your hand and identify yourselves? And something we wanted to do is to encourage everyone to meet new people. So folks, please meet at least one new first timers. Okay. If you haven't done so, make sure you do that by the end of the after the presentation. So talk with someone new and let them all feel welcomed at this meetup. So and also I'm gonna open up the floor for anyone to make the announcement, as I just mentioned earlier. I think Jens is gonna make an announcement.
Yeah.
Yeah, please go ahead.
So I was going to share that for anybody who doesn't know, we have a data conference coming out next Saturday. It's part of Music City Tech, which started off several years ago as Music City Code. It was focused on developers and kind of a polyglot developer conference, technology agnostic. Nashville's kind of a .NET Microsoft heavy town, so there's a little bit more of that. We started adding Music City Agile the next year, which is focused on agile methodologies. A lot of PMs and BAs to come out for that content specifically. And this year we're adding Music City Data. And Kevin Klein is a speaker. He talks a lot. He used to write articles for SQL magazines. So he's heading up this conference, and our objective is actually to cover more of the data science and the big data topics, but we've also got a pretty good basis of data storage platforms and analysis techniques. So check out the content. If you go to data.musiccitytech.com, you can see the session schedule. And, actually, I was going to give away a couple of all access passes to the event, just to get you into all 3 conferences. And I pulled the names from the Meetup RSVP list. So if you RSVP'd for tonight, you're included in this drawing. And hopefully, we don't get too many people who didn't show up. Because of the way I pulled this in, I've got 227 lines in my spreadsheet. So somebody give me a number between 1 and 227. Anybody? 14. 14? All right, let's see who 14 was. Ryan Tuck?
That's me. I already have a ticket to the data conference.
Okay, well now you have an all access pass to all the
Okay, I would not be offended if you wanted to re-wrap.
Okay, if you want to give away something else?
Go ahead. I think I can only make
Pick
the
the next random number.
200.
Semi-random. 200. And that would be Mark. That's a Greg? No? What? All right. Have another.
100.
100. Vishal Patel? Vishal?
Check's not
That's number 1.
Chinzai Tian?
Oh.
You pick the hopefully last name. Thank you. Sorry?
I'm sorry.
Just give
yeah.
Okay, I was asking if you wanted to pick a number. What was it, 200? 212. Reed Wang?
Oh.
Tickets for the data conference are $80. If you have a group of 5 or more, you can get 20% off. Thanks for letting me share.
Yeah, absolutely. So, does anyone else want to make any other announcements? John?
Yeah,
Go ahead. Yeah.
The speaker is out over next year.
Oh. Awesome. That's great. Okay. All right. Then we're going to learn more about this algorithm. So without further ado, I'd like to introduce our speaker, Chris Fonnesbeck. And, we're all in here tonight for a treat because he is the creator of PyMC. He's now an associate professor at Vanderbilt University in the Department of Biostatistics. And he hailed from Vancouver, Canada, and got his Ph.D. from University of Georgia. So I'm not take up more time and just gonna let's all welcome and give it up to Dr. Chris Fonnesbeck.
Thanks everybody for coming. That's great to speak at this meetup. I've been to a couple of them myself. I always plan to come to more than I actually get around to attending. Hope to try to get out to some more in the future. And I've been privileged to talk at a lot of these meetups in different places, both inside and outside of the United States. And it reminded me, around this time last year, I gave a similar talk to the Bayes meetup in London. And it's a fun meetup because, of course, in England, what you do sort of before or after the meetup is, you go to the pub, right? And after this particular meetup, the pub we went to is the Artillery Arms, which is in East London in Shoreditch. And maps down here. And if you're sitting in this window and you look out that way, there's a graveyard called the Bunfield Hills Cemetery. And if you walk in the front gate and turn the first corner, the big tomb that you see right here is where Thomas Bayes has been. So it's cool to give a talk about Bayesian inference with Thomas Bayes being like just down the street. So take a little of your Guinness and pour it on them. They don't like you to do that. But so anyway, so I'm going to talk a little bit about probabilistic programming, and I guess a good place to start there is to kind of define it. Probabilistic programming is not new. The term is new. We've sort of come up with new names for things, data science and probabilistic programming being two of them. And when we talk about a probabilistic program, it's any program that is at least partially dependent on random numbers, which isn't hugely useful. But the important thing here is that the outputs from your program aren't deterministic. There's a stochastic component to them, and so. But that definition tells you that you can use any language to build a probabilistic program that has a random number generator. Sort of a more useful way to think about probabilistic programs is in terms of what the primitive variable, the primitive types are, if you like, of that language. And what probabilistic programs do is they essentially add a new type of primitive. So rather than just ints and floats, we now have sort of stochastic primitives. So random number generator based primitives, and we use these as building blocks for building stochastic programs. And so each of these primitives have the ability to draw random numbers, random values, and use those values as part of its implemented. And these are random numbers or pseudo-random numbers. The ones you just generated are arbitrary numbers. And if, so, for example, this is just sort of pseudocode here. You can use a stochastic primitive to represent, rather than just a single value, a scalar or a vector-based variable, you have now a variable that is a norm, for example, or some other type of distribution. And that distribution can generate different values, right? So we can draw, 100 out of that X, for example. You can do more complex things. For example, you can have distributions over entire functions. We'll talk a little bit later about Gaussian processes, where now the thing that is instantiated, or the thing that is generated every time it's called, is an entire function, not just a single value. And importantly, it allows for conditioning between variables. So you can link up variables in such a way that have a Bernoulli random variable, a 0, 1 binary random variable that has some probability associated with it, p, and that p in turn can be another stochastic value. You can link these things up and use conditioning to express quite complicated and complex models using these sorts of stochastic building blocks. So that's kind of what probabilistic programming is. Okay, think of it as different additional primitives to your programming language. And of course, the reason that we do probabilistic programming nowadays is that it facilitates the application of Bayesian methods. And how many people have built a Bayesian model before somewhere? So less than half, though. So I'll do kind of, compress an entire Bayes course into 10 minutes here. Talk a little what Bayesian inference is. The important thing to remember about Bayesian inference is that it uses probabilities like any statistical does, but it interprets probabilities slightly differently. Classical statistics, probably the statistics when you were in school, either graduate or undergraduate. And in particular, Bayesian inference uses probabilities to describe the state of knowledge regarding something that's unknown. So it's a subjective probability. So it can change from individual to individual, state of information to a different state of information. And what Bayesian inference involves is the calculation of inverse probability. So the notation I'm going to use here is so in the world of Bayes, there are only classes of things, unknowns and knowns. Okay? Everything that you put into a model can be classified as something you know and something that you don't know. I'm going to use theta to represent things you don't know, so parameters in a model, for example, but it can be other things. The probability a hypothesis is true, a future value that you're trying to predict from your data set, anything that's unknown. And then the stuff that we know is typically our data. So, Y will be observations. And so all of Bayes is concerned with calculating this, the probability of something we don't know given something that we've observed. And this is a conditioning statement, right? It's something we don't know conditioned on something that we don't know. And these things that we don't know are typically stuff we care about. Okay? It could be unknown rates. It can be, again, occurrences of new data. They can be things that we don't care about but are still unknown, and we need to calculate them in order to build our model. Nuisance parameters, for example. That's kind of the idea. So, but why do we do that? Why do we need a new type of probability, a new statistical paradigm in order to solve problems? Well, for a lot of us, these methods is because they solve problems that traditional methods couldn't. Models that are far more complex using Bayesian methods than I could before. Part of this, it's sort of an ironic thing, is that your ability to build and solve more complicated models stems from the fact that Bayes is built up from very simple building blocks. That conditioning that I told you about, you can break up a big complicated model with lots of parameters using conditioning statements. And it gives you a really flexible, powerful toolkit for problem solving. This is a quote from Lincoln Barker, who wrote a book on Bayesian inference for ecology back in 2010. And part of the simplicity is that things in Bayes are traditional statisticians You know, if you go into my office and you visit a random statistician, who is not a Bayesian, they're sitting in their office coming up with estimators for things, right? An estimator for an odds ratio, an estimator for something, and you have to do that de novo every time that you come up with a new problem. In Bayes formula is always your estimator for everything. So theta is really anything you don't know that you want to solve that you can write down in a model. And so the kernel of this is the fact that we are doing an updating procedure. So on the far right-hand side, the probability of theta is the probability of the things we don't know before we need data. And we call this a prior probability. What we're trying to get to is a posterior probability. So we're going to add data somehow. And the way that we add data is using what's called a likelihood function. So the probability of y is theta. So the data we observed given numbers. And we use that to update what we know. Aren't probabilities in the sense of that we think of when we learn probability in school. So probability of, you know, sort of coin flips, things like that. Probabilities of getting, you know, an ace out of a deck of cards. Those are frequentist probabilities, right? These are a state of knowledge. So this is just a very general rule for learning from data. And the nice thing about this is that when you're done, and you can go out and collect more data and use your posterior from your previous experiment in a new one and update it some more. You get some more data. So you use your posterior as the prior the next time you go out and observe the world. And you can keep doing that. And hopefully you keep learning every time that you do it. Now, one of the big advantages of a Bayesian approach to inference and prediction is that all outputs from probabilistic programs are entire probability distributions. They're always in probabilistic terms. So you automatically get a measure of uncertainty about what you're trying to estimate, and you're able to answer sort of arbitrary questions about what you're trying to understand. So here, for example, this is I work on epidemiology a lot, so this is a co-infection effect, so the effect on, say, a severity of a disease if you have another infection. You can say, well, what's the probability that this effect is greater than 3? You can just integrate from 3 upwards, and you get that probability. You can say you can get a probability interval, which is different than a confidence interval, that is a probabilistic statement about the true location of that parameter in sort of frequentist terms. So it's really nice. You get all of this for free if you're able to come up with a way of turning that Bayesian crank. And what I'll talk about today mostly is turning that Bayesian crank. So when we're specifying how do we do this? We specify a probabilistic program. What does that look like? It kind of looks like this. You're specifying a joint of your entire model. So the first step in the Bayesian model, probabilistic. So the things you don't know, the things you know. Okay? And there can be hundreds, thousands of parameters. There can be lots and lots of data. And we break it up using conditioning statements. Okay? So there's a component having to do with how your data fits into your model. You have to specify priors for the things that you don't know. So what do we know about our rate of disease, probability that somebody is going to turn to your website, whatever that unknown thing is. So there's two steps. Specifying your likelihood, how the data fits in, and then the priors. And I'm going to talk a little bit about how you think about that. So the first thing are prior distributions. So prior distributions quantify the uncertainty in the latent variable. Latent variables, just unknown variables. And so, for example, we could specify a normal distribution around something, center it at 0 and have some variance. And this kind of described we were pretty certain the true value is somewhere between -3 and +3. That's kind of the information, the prior information that we have. This is also a normal distribution right here. It looks very flat. This is a normal distribution with a variance of 100. And so this isn't quite what we call an uninformative prior, but it's a very vague prior. It's saying we don't know very much about the true location of that parameter. We may have different ones depending on the type of unknown. So for example, let's say I'm modeling the probability of contracting a rare disease. Well, we know a little bit about this, right? It has to be between 0 and 1, because a probability is between 0 and 1, and it's a rare disease. We've just said it's a rare disease, so maybe it's less than 10% without any other information about that disease. So you can specify something like a beta distribution with a big value for the the beta parameter, and that would represent that. So some rare disease prevalence. Let's say we're a geneticist and we're doing experiments. Output is the variance in the widths of the fly wings, right? Something like that. Well, you don't specify a big wide prior because fly with wings are very tough. So log normal that specifies some prior information here. Okay, any sort of prior knowledge that you have, prior is a bad name early on because it gives the impression that you can kind of specify whatever you want for your prior and make your analysis do whatever you want. But that's not quite true. You have to explicitly say which priors you're using. So if you're using a very informative prior and it skews your results, there's really no way of hiding that. But also, if you do have prior information, if you do have information from other sources, the goal here is to get the right answer, right? It's to get the true estimate. You're best to bring all the information you can, both in your data and outside of your data. Another way of thinking of prior is kind of as a population distribution. So interested in sabermetrics, calculating, say you're a baseball fan and your favorite player has just got hits in his first 3 at-bats of the season. Well, what do you think his average is going to be at the end of the season? Well, it's not a flat prior between 0 and 1,000, right? The population distribution of batting averages since the turn of the last century is it has a mean of about 26%, 260. It gets as low as about 0.15. If you're below that, you're not in major leagues. And it's really, really hard to hit above sort of 300, certainly 350. So everybody's in here. There's really no chance of you batting 500 for the whole season or batting 0 because you wouldn't last. So these are sensible priors. You're not importing huge amounts of information. This only describes population. The next part, so that's priors. The likelihood is how the data gets in. And likelihoods are not controversial. Likelihoods are used in frequentist inference as well as Bayes. The thing is, you choose the likelihood just like you choose your prior. So it's all subjective. All statistics is subjective. It's all subjective choices. So there's nothing particularly subjective about priors. What we do now is we condition our model on the observed data. Well, what does this look like? Well, of the normal data, normally distributed data, this would be something like individuals' heights, birth weights of newborn babies, something like that, distributed with some mean and variance. And this describes now our data, right? Not the uncertain. Parameters are here. These are the things that we're trying to estimate. So now it's y given, sorry, I should call this y rather than x, but it's data given parameters. In the case of our baseball example, well, 0, 1, every time you either get a hit or you don't, you have 5 at-bats a game, and the thing we're trying to estimate here is P, or probability of getting a hit, okay? And you might have prior distribution. So you specify all your data, all your data, as well as your unknown parameters. Website visitors per month, for example. So the kind of the art to Bayesian inference is becoming familiar with probability distributions and both things you're trying to estimate. How many cars pass through an intersection during rush hour every day, things like that counts. Okay? All right, so having done that, what we do is we try to combine the prior and the likelihood to get this prior. So this is the holy grail, is getting prior. And this is sort of a short form of the Bayes formula. It's kind of a, notice I didn't even mention the denominator of Bayes' formula before. I kind of glossed over it because it's ugly and it's hard to calculate. All it is really is a normalizing constant, right? It makes sure that your posterior is also a probability, just like the things that you put it into it. It's the probability of y, the probability of your data, which is kind of a weird thing. Probability of data. Well, it's the marginal probability of your data. It's your data integrating out all of the unknowns. Okay? So it's the numerator integrated over all of theta. So you can do integration by hand if it's like, if you have a model with one variable, you can do this. I have trouble doing two variables of parameters or even dozens. You can't even do this, right? You can't just calculate this in closed form. So we typically require numerical methods to approximate this posterior distribution. This is one of the reasons Bayes learn in school, at least when I went to school. Maybe now, hopefully they're teaching more of it. But it requires sort of powerful computing most of the time. So what probabilistic programming does is it abstracts all of that, right? It allows us to not work that we use to estimate posterior distributions. It gives you kind of a high-level interface, if you like, to Bayesian inference. And again, I said probabilistic programming is not new. Statisticians have been doing this since the 90s. There was a language that sort of I grew up with in school called WinBugs, and this came out of University College London, Imperial College London. That's actually where I gave that talk last year. It was pretty exciting to be in the home of WinBugs. And it was revolutionary at the time. It's sort of Bayes for the masses. Okay, I remember as a graduate student asking another scientist for their answer doing. I was an ecologist. It was a model for this, and that's no fun. WinBugs gave us a nice graphical user interface for building Bayesian models, and it was, you know, this like cockpit here. You could enter in all of your preferences and watch the sampling live for all of your parameters. It was pretty cool, and it made it easy to describe and share Bayesian models. So not just high-powered computer programmers, statisticians could build Bayesian models. Anybody could, biologists, and so on. And the important thing is that it provided a domain specific. This probably looks pretty familiar. This is not R, this is bugs. This is the bugs language. It's, you know, a way of specifying priors and likelihoods and transformed variables and so on. And so in 6 or 7 lines, you could specify a nice model and fit it. And that was great for a while. There are some downsides to WinBugs. It was closed source, which, you know, open source wasn't quite as big of a thing back then. There is an OpenBugs now, but we like to think of it. You've got to kind of ask permission for it, and the guy who holds on to it doesn't really like to give the code away. Once you do have it, it's written in Object Pascal. How many Pascal programmers in the audience? Oh, what? Okay, it's 5. Wow. Okay, that's more than I usually get. So most, you know, even if it was on GitHub, there probably wouldn't be many contributors to it. And it's also just domain-specific language. So you know, if you're building a model in Python or R, you've got to get your stuff into WinBugs, and then you get your stuff out of it, and so on. So, so when I was back when I had spare time, when I was a postdoc at the University of Georgia, and I was learning Python, I decided to kind of scratch my own itch and try to see if I could build something similar to WinBugs using an open source language. And so I created a package called a PyMC. And sorry, this is hard to read on the screens probably from where you are. This was back in 2003. And the motivation was the same. I wanted people to be able to specify arbitrary models, not specific classes of models, but arbitrary models in Python and fit them. That was 2003, it's now 2018. The current version of PyMC is PyMC3. The previous version of PyMC was built on Fortran code. So if you go to the PyMC GitHub repository, it actually shows up as a Fortran project, because it's mostly Fortran code with a little bit of Python on the outside, so people don't have to use Fortran. In the last couple of years, we switched our back end to use the Theano machinery to do probabilistic programming. And the reason we do that is that it implements what I would call next generation Bayesian inference methods. And these methods that I'm going to describe in a bit require the calculation of gradients over your model, so derivatives over your model. Not as hard as integrals, but derivatives are hard too. But all of the thing that all of these deep learning packages do is they can calculate automatic differentiation on vectors, which is great. That's what we do. And there's now over 100 contributors to this project. It's the nice thing about the open source model is that if you have a good idea at all, it attracts people smarter than you and more talented than you, and that's exactly what happened here. And PyMC3 is really good now. It's used a lot in academia and industry. Companies like Allianz Insurance, Monetate, Channel 4 in Britain. We are always folks that are using it. And we published a paper about it in 2016 that describes it. It's a NumFocus sponsored project. And NumFocus is just a nonprofit that supports and promotes open source scientific computing in sort of a sustainable model. It kind of aims to increase the collaboration and communication within the scientific computing community. You see lots of projects that you're probably familiar with. Jupyter is a NumFocus project, Pandas, and some non-Python stuff like Julia and so on. So it's a very robust organization, and they do a great job, and they help us out quite a lot. So as I mentioned, Theano is kind of the engine behind PyMC3, and again, the big thing that it does for us is it calculates gradients. It's very similar to other toolkits for deep learning like TensorFlow and Torch. It was created by the LISA lab. It's now called the Montreal Institute for Learning Algorithms in Montreal. It's Yoshio Bengio's lab. And what it does is it does kind of dynamic C code generation. So just doing a kind of a simple problem here, kind of looks like this. You import things like tensors and functions. So we're going to create tensors, which is just a generalization of a vector. So different tensors can include an array, a matrix, or tensors of higher dimension than 2. So we might create a matrix and call it X. Notice I haven't given it a value yet. I could transform that. This is a logit transformation, so transforming something to the 0, 1 interval. And then the magic is, if I need the derivative of that, I just call grad, and I get derivative of that. And then I can create a function for doing the logistic transformation of a matrix. The thing about this is that no calculation has been done yet. Okay, this is a delayed execution model, lazy execution model. Nothing's happened yet. All I've done now is I've built a graph. So underneath this, Theano's building a graph, a static graph that it's able to optimize, and it uses that graph to be able to calculate the gradients that it needs. So you can always go in and look at the graph. They're usually ugly like this. They usually don't help you very much, but it's comforting to see that it's doing something. And then now, when you actually call that function that you built, that's when it compiles The C code is generated in piles, and then it runs. And so I can pass it actual values for a matrix, and it gives me the logistic transformation of all the elements in that matrix. It's not a very useful example. It's just kind of illustrate what Theano does. Just like with Fortran, nobody wants to look at Fortran. You typically don't want to look at Theano either if you're an applied user. So PyMC, one of the things we try to do is just hide that as much as possible so that you're programming Python most of the time. But that's kind of what I like to give people a little bit of a peek under the hood. Theano was recently discontinued. I think they just, with Theano's kind of run its course. It's kind of done its job. It's simulated the development of deep learning frameworks, and now everybody's got one, right? Google's got TensorFlow, Facebook's got Torch, Amazon's got MXNet. There's lots of these things, and Theano eventually won't be able to keep up. It's still generally faster than any of those and more capable. It's been a really good platform to build on because it's been so stable and performant. And so in future versions, we're going to move away from Theano, but for now it's doing a great job, and we're probably going to maintain it in order to keep PyMC3 going. What about a Bayesian model now? Now that we know, what's going on, I'm going to show you how PyMC works by building a simple model. This example comes from one of Andrew Gelman's books. This is the radon exposure example. This is a kind of environmental epidemiology example. So radon's a carcinogenic gas, inert gas, colorless, odorless, and it's the primary cause of non-smoking related lung cancer. And so what it does is it kind of seeps in through the groundwater into your pipes of your house, and so on. My house, I live in East Nashville, we took radon remediation. So we now have a little fan that kind of blows the radon out into our neighbor's yard, and so there's kind of things you can do to lower the. So you don't get cancer obviously right away, but it's if you're exposed to it over the long term, it has a higher risk. And so there's a big database, an EPA database of radon within houses that measured within houses, and of course this is going to vary over time and space depending on what building practices are going on, what there are variables like how much uranium is in the ground, and so on. And so let's say we want to build a model to estimate, predict things about radon contamination. And so the database I'm going to look at here is from Minnesota. It uses 85 counties from within Minnesota, and then houses with basements have a higher probability of having radon. So you can account for the fact that some houses have basements and so on. And there's a few different ways of approaching this problem. One is, at least in sort of a traditional sense, one is what we would call a pooled model, where we would say there's some underlying parameter, theta, let's say the mean amount of radon, expected amount of radon in a particular house, and that's driving all of the observations. Okay, so there's some random draw from a distribution with these parameters. Okay, so what it's saying is that everything's alike, right? We're pooling everything together. So it allows us to combine data, but it glosses over a lot of heterogeneity. The alternative to that is doing an unpooled model. We could say that every county has its own theta. All these counties are different. We can't say that they're the same and pool them. And so now we have k parameters and k data points, and that accounts for this heterogeneity. But you take a hit on your sample size. Not super satisfying because these counties are adjacent to one another. They're all within the same state. They're not that different. They can't be pulled together. What you get if you try to fit models like this are kind of two extremes of a continuum. And so the red dotted line here is the pooled effect. So they'll be the same in every county. And the blue line is the estimate from the unpooled model. And you can see, St. Louis County had a lot of observations. This is the effect of floor versus basement. These are the radon measurements, essentially. And you know, these are all essentially pretty close to the overall mean. But then you get some, like Black and Pearl, which, you know, has a very small sample size, but very extreme values. And so we don't know whether to believe that estimate, right? There's only 2 data points. But those 2 same data points could have come from, you know, so, you know, the pooled model is kind of unsatisfying because we can't, you know, use it to, you know, if we're trying to identify high radon counties, a pooled model is useless to us, right? If we say everything's exactly the same. But we don't trust these unpooled extreme examples. What we can do in a Bayesian context really easily is turn this into what we call a hierarchical model. This is where we can use that conditioning that I talked about earlier. What we can say is that the parameters, this county level parameters, are themselves members of a population of counties that are drawn from some other distribution. So we can say that the radon parameters for all the counties in Minnesota are drawn from some superpopulation. Okay? And so this is known as a partial pooling model. So every county has its own parameter, but those parameters are constrained to come from the same distribution. And so what we're really trying to estimate are these, the hyperparameters of this model. Okay? And so we can write down, you know, a simple hierarchical model like this that models the observed amount of radon as, let's say, some linear combination of a county level random effect, floor, you know, a floor effect here for whether you have a basement or not, and then it allows for some, you know, random error for things that we haven't measured, but we want to include in our model. As good Bayesians, we just write down our probability model, which put priors on the unknowns, the regression parameters in this case, and we use a normal likelihood, because at least the log radon values are normally distributed. We wrote down our model. The next thing you have to do is, you know, turn that into code. And so PyMC code kind of looks like this. We instantiate a model object, and we put that model object inside of a context manager, Python context manager, this with statement. It's often used for things like network connections, manage network connections and shut them down nicely when you're finished, or opening a file. We're going to use it to populate a model. So any PyMC variable that's declared inside this context manager gets automatically added to the model. Remember what Theano is doing in the background is it's building a graph. So we're going to build a graph, but PyMC is going to do it automatically for us. And so what we really do is we write a line of code essentially for each line on the model here. So the kind of the overriding goal of PyMC was to make coding a model as simple as writing it on a whiteboard. That's kind of what our goal was here. So same things happen here. We specify priors for the hierarchical components of the model. And then here's the random effect for the intercepts. So these are county level intercepts that have hyperparameters mu and tau. And there's our floor effect, which is beta. So that's all our priors. And if we look at some of these guys, so if we go in and look at beta, oh, by the way, we're allowed to, if you're using Python 3, you can use Unicode characters. So you can use Greek letters, specify variables, which is really nice. And if you're using Jupyter or IPython, if you do /beta, you use LaTeX, hit tab, it will turn that into the Unicode characters. So it's pretty cool. So if we look at some of these now, we can inspect it and see that it's a free random variable type. So this is essentially these that I was talking about. And these types have attributes associated with them that are useful. So it's got a distribution, which we specified as normal, and we can do things with it. We can calculate its log probability of some arbitrary value. I just put -2.1 here. And then eval does the compile and run thing, because this is delayed execution. I can draw random values from it, and so on. Okay, so this is the probabilistic programming side of things. We also allow for transformed variables. So the theta, the predicted value of radon in a particular county, is just the sum of the county-specific intercept plus the floor effect. So we just get a transformed variable just like that. And then our data likelihood is normal. The way we specify likelihood is we just pass it the data. data are observed. These are the log radon levels. So that's the only thing that separates a likelihood from a prior, is that the likelihood has observed values. And what that's really doing is it's telling the Bayesian model not to change the values of that parameter, right? That's really the only thing that's going on, is that you observe this node in the graph and it doesn't change. It's not stochastic. Stochastic before we observed it. Now that we've observed it, it's fixed, and we're conditioning on it. All right, so we're done. We just have to calculate posterior distributions. And so this, remember, this is the hard part, because we don't know how to turn that proportional sign into an equal sign, because the denominator is ugly. And over the years, there's been a variety of ways proposed to approximate that posterior distribution. Things like just sheer optimization of an unnormalized posterior. You can do that. You can just throw BFGS at it and get the mode, the posterior mode. The problem with that is you don't get anything but the mode. You don't get any estimate of uncertainty, so it's not really a fully Bayesian approach. You can do things like rejection sampling and importance sampling that are approximations, likelihood-free approaches like approximate Bayesian computing, but the sort of the de facto standard for doing Bayesian inference is something called Markov chain monitoring. If you thought my description of Bayesian inference was short, just wait till you hear my MCMC explanation. You get one slide. So two MCs here. One is Markov chain and the other is Monte Carlo. So MCMC simulates a Markov chain. That's really what it's doing. It's generating a Markov chain using Monte Carlo approaches, so random number approaches. But it generates, so a Markov chain is just a stochastic process where the current variable is dependent on the previous value of the variable. Or if you like, the next variable is dependent on the current value of the variable. So they're not quite independent. They're sort of one step dependent on one another. So it's impossible to sample from this model independently, but we can, it turns out, sample from it dependently. So the key to MCMC is that if you can construct a Markov chain with particular properties, then simulating that Markov chain will generate a posterior distribution as if you were sampling from it independently. And the condition that you have to satisfy is something called the detailed balance equation. And it simply balances movement over, if you think of that distribution, what we're trying to do is explore the distribution. So unlike optimization is just trying to climb the hill, get to the top, what we want to do is explore. So it's balancing movement in and out of high probability regions. Okay, so the key, MCMC, build, and you're done. Just sample from it. You have theoretical guarantees of getting your true posterior distribution. So MCMC is kind of a catch-all class of models. It's not the name of a particular algorithm. The popular one kind of over the years is Metropolis sampling. There are other flavors like Gibbs. Stands for Gibbs sampling, Bayesian inference using Gibbs sampling. It's a special case of Metropolis sampling, but just to give you an idea, the Metropolis algorithm is very simple. You initialize, arbitrarily initialize all your parameters, beta to alpha and so on in the class model. And then you propose a new value for those parameters. Propose it any way you like. And then you evaluate those newly proposed values relative to the values that they currently have. And you either accept or reject them. If it's a good value, you accept it, and you go back and you do it again. If you reject it, you revert to the current value. So you take another, you put another of your current value onto the chain, and then you go back and do it again. So it's accept, reject, accept, reject, accept, reject, okay? Over and over again. And what it starts to look like is this. It's a 100-dimensional and you can see what's happening here. You can see, you know, it kind of stops every now and then. It kind of gets stuck, lots of rejections. And notice that it's not even exploring the whole space. It's not even getting to the meat of the distribution here. It's sampling for larger models. It's almost impossible to get good answers for big models this way. And that's what you were getting if you were using bugs or JAGs, things like that. And this sort of it typically requires sort of tens or hundreds of thousands of iterations to get a good answer, all sorts of convergence issues. Served us well over the years to fit sort of small to medium-sized models, but it doesn't do a great job for larger models. And that's what kind of stimulated the need to do kind of, again, what I would call next generation Bayesian methods. And this is what involves using the gradients that I told you about earlier in Theano. Hamiltonian Monte Carlo is an improvement on the Metropolis algorithm in that it doesn't do kind of a random walk. It doesn't randomly propose values. It proposes good values based on the gradient. Right? So it tries to find areas of high probability in the parameter space, and it will tend to go towards those. What it does is it uses a physical analogy of a frictionless particle moving on a surface. So you can think of your model, your parameter space as being like a, skateboard park, right? And think of your particle as being a skateboarder. What does it do? It kind of follows the gradients of the space, and it kind of explores it. It might go up one side and back down the other again, and then you stop and sample a point. And then you go off in another direction, and you sample again, and so on. And so it follows the kind of the landscape, if you like, of the model. And so you use this. You use an auxiliary variable to represent the momentum of the system. So you're modeling position and momentum, simulating this Hamiltonian system. So the idea here is that what you do is you start with your particle and you sample a random velocity. So just sample from a normal distribution of velocity, how hard you push the skateboarder or flip the ball on the surface. And then the key here is that what we're doing is we're simulating a continuous system using discrete jumps. So you got to do the series of steps called leapfrog steps. So it does this kind of leapfrogging step until it gets to essentially, the top of the skateboard park, and then it'll stop, and that's your point that you sample. Okay, you follow the gradient all the way along. You do an accept-reject step up there, and then you do it all over again. You push the ball down again, and you take another point. Okay, that's the idea. It's a more complicated algorithm. This is a total caricature of it, but of course we're limited on time. And but the goal or the result of this is that you get much better proposed values, and you get a much more efficient algorithm. So the same 100-dimensional Gaussian proceeds like this. Okay, it's easily covering all of the parameter space. It's having very high acceptance rates, much more efficient. Okay. So, and one of the drawbacks of this is that with Hamiltonian Monte Carlo is that it's got a lot of tuning parameters. How big are my leapfrog steps? When do I stop? I could let this frictionless point stop and take the sample. All of these things have to be tuned. Andrew Gelman and one of his graduate students, Matt Hoffman, came up with a Monte Carlo called the NUTS algorithm, the no U-turn sampler, and that's just in reference to the fact that it tries to stop that particle before on that skateboard park, right? It gets to the top, and then it wants to come right back on the path that it came. So what the algorithm does is it recognizes when it's about to do a U-turn, and then it stops the sampling there. And so this is the algorithm that PyMC3 uses. And hidden from you, all you do is you take your model, you call sample on it, you tell it how many draws you want, how much you want to tune it for, and it goes off and it does it for you. So it's, again, abstracting all of that stuff for you. Okay, and again, you get some nice output here. So these are estimates of the parameters for beta 1 and beta naught. And for the hierarchical model, you get much nicer estimates. So these are the hierarchical estimates of each of these counties. You can see now the one we didn't trust very much. What's essentially done here is it shrunk that estimate kind of towards the overall mean. That's what partial pooling does, is it shares information between all of the elements in that random effect. So it's saying, yeah, lactopro could be very different from the others, but it's probably not. This is probably sampling error. So you sort of hedged your bets a little bit. So you get much more realistic estimates here. Problem is, though, even with more sophisticated algorithms, MCMC can still be kind of slow. It's not for big data. It doesn't scale well with n, your sample size. And you know, we're in the age of sets, if not big data. What we can do is turn to alternative algorithms that scale a little bit better with sample size. And the one that PyMC uses is something called variational inference, which I'll talk about just for a couple of minutes. What this does, instead of sampling, is it turns the whole problem into an optimization problem. And what we do instead is we take an approximate distribution, one that we're very familiar with, like a normal distribution, and we use it to approximate the true posterior distribution. And the way that we approximate that is we optimize the parameters of that approximating distribution so that it's as close as possible to the true posterior distribution. And the way how we define closeness is in terms of what's called information distance. We use a metric called that distance, which is an information distance between, in this case, two probability distributions. So Q is our approximation, P theta given Y is obviously our posterior distribution. And the nice thing that it does is that it gives us an expected value, which is our, again, a normal distribution that we know how to take expected values of. There's a problem in that it involves the true posterior distribution that we don't have. So what variational inference does, rearranges this a little bit, it comes up with a quantity called the elbow, the evidence lower bound. And minimizing the Colbeck-Lagler distance is the same as maximizing the elbow. And that's essentially what happens. There's a really nice algorithm that automates, just like nuts, auto-tunes, Hamiltonian, Monte Carlo, automatic differential. It's like picking a distribution that covers all of the parameter space, transforms your parameters for you so that it can be optimized properly and so on. So it completely automates all of this stuff. And so what you get is something that sort of looks like you're doing MCMC, but this is just an optimization. We're trying to maximize the evidence lower bound. You can see that it hits something, right? Some sort of ceiling. It does as well as it can given the approximation. And it works quite well for a lot of things. So this is estimating a beta 147, 255. So the true parameter distribution is that black dotted line. And this is what ADVI does for 10,000 iterations. It finds that posterior distribution, at least for this simple example. All you do is, instead of sample, you call fit. And N here is just the number of optimization iterations. They tend to go faster. You can specify your favorite optimization algorithm, and it runs. This one tends to be pretty fast. And what we get here is an approximated distribution. It's really nothing to look at, but we can sample from it, right? So we can sample from that approximated distribution and get estimates for, in this case, it's mu and sigma from a normal distribution. So it ends up looking a lot like MCMC, but it's more of an approximation. Of course, you know, just like in machine learning, there's no free lunch. When you approximate, you know, you sacrifice something. So what you often get is an underestimation of the variance. Because the approximation used tends to be a mean field approximation. It means that it's treating all the variables as independent of one another, and that's usually not the case. And so you can tend to underestimate stuff. But, you know, if you've got a million data points, it does allow you to scale stuff. And you can get more robust algorithms that make fewer assumptions about the model that you can use as well, and PyMC gives you some of that also. And the other nice thing you do here is you can mini batch. So Theano will allow you now, rather than hard values as our data, we pass shape. So what mini batch is going to do is it's going to, at each iteration, take 50 randomly chosen values from the data and substitute those in and under the ADBI algorithm. And then it will fit a lot faster. It will fit faster and it will generally be more robust because it's doing stochastic gradient descent. So it can avoid local minima and so on. I was going to talk about Gaussian processes, but it's 8 o'clock. So I'm going to speed past it. We have a really nice Gaussian process module for PyMC. And this is just a way of fitting non-parametric models in PyMC, where again, rather than sampling scalar values, we're sampling functions. And this is a really nice flexible way of doing what you might otherwise use, say, a spline function. To do Bayesian machine learning. So machine learning algorithms are typically very data hungry. They can be very poor at representing uncertainty. And Bayesianizing a machine learning algorithm priors on the unknowns. So this is a simple example that you can actually find in our sample notebooks in the PyMC project. This is a Bayesian deep learning algorithm in 3, 4, 5, 6, 7 lines of PyMC code. And so all we're doing here, this is a 2-layer neural network, so it's officially deep. And what we do is we put weights on the nodes, on the nodes of each of the hidden layers. So here we're putting normal 0, 1 weights on those. And then a binary classification problem. So what we're doing is we're trying to get this separating. So these are Bernoulli classifications into red and blue. Right? And figure over here is interesting because what we're showing here is not the separating hyperplane, but we're actually showing the uncertainty. This is the posterior predictive standard deviation. The more uncertain we are about our classification. And that's the thing that you don't usually get with a typical neural network. You either get classification yes or no, at best the probability of classification. Here we have decision boundary. The future, we have some Google Summer of Code students this year that are going to contribute quite a lot, we think. Approximate Bayesian computing is one of these other algorithms for approximating posterior distributions. We have a student, Agustina Adriello from Argentina, working on that. Scalable Gaussian processes. Again, I didn't have a chance to get into GPs. Bill Engels from Oregon State University basically wrote all of our GP stuff himself last summer. It was very impressive. Now he's going to try to make it faster and more efficient. And then the big one is that we've got a student that's going to begin the process of PyMC, hopefully coming up with some prototypes for that. This will be PyMC3. So PyMC3 will always be Theano until PyMC3 isn't worth using anymore. Again, all of these other at the moment, but the future will be different. And so we're going to start developing PyMC4 as part of Google Summer of Code. If you want to play around with PyMC a little bit, our GitHub repository includes a whole bunch of sample notebooks with tons and tons of well-documented, robust examples. There's the Bayesian neural network, survival models, Gaussian process models, it's all in there. If you don't want to use PyMC for some reason, we live in a great time. Back in the 90s, WinBugs is all we had. Well, today, these are just the Python tools for doing probabilistic programming. You can use Edward, which is now part of TensorFlow. GPy or GPFlow for doing Gaussian processing. Stan has a Python interface. MC, base pi. These are just the ones I thought of. There's more. And if you want to learn more about probabilistic programming in general, there's a really nice open source online textbook written by a guy named Cam Davidson-Pilon. I think he works for Shopify these days. It was originally written under PyMC2. A couple of folks have recently ported this to PyMC3. So all the examples are now in PyMC3. You can go through this if you want to learn. You know, I didn't do Bayesian inference nearly justice in this talk. So if you really want to dig into it, this is a good place. I just want to thank this is the kind of the core development of PyMC3 at the moment. It's incredible, again, how it's grown over the years. PyMC1 was just me. PyMC2 was me and 2 other guys. And PyMC3 is this plus dozens of other non-core contributors. And if you have any inclination whatsoever, even simple stuff like writing documentation or finding problems with our documentation or bugs in our software, we invite you to come in. We have a discourse page now for discussions, and I think our group is pretty welcome. So at least give it a try, and if you're so motivated, please come and contribute. And if there's any time left, I can answer some questions, but I'm done. Thanks.
Thank you so much, Dr. Fonnesbeck, for this really engaging tour of PyMC. I think we have time for about 2 to 3 questions. If you have more questions, feel free to stay and talk with our speaker. Also,
would the variational inference approach significantly have changed the way you did the exam? Simply have coded it.
You can. The nice thing about it is that the model specification and the fitting are completely independent. So you can take any model and you can fit it using maximum a posteriori, that's just the optimization. If you just want the means or the modes, you can use MCMC. You can use variational inference. There are some constraints, you know, like variational inference requires only having continuous variables. So if you've got discrete variables, your data can be discrete, but the unknowns have to be continuous. So, you know, not everything works equally well under each algorithm, but anything algorithms are independent of model specification. So I wounn't have to change my model. That's nice. So like scikit-learn is really great, right? One of the reasons it's great is that you have your model and you can throw, you know, you can throw it at a SVM and you can throw it at a random forest and your data, and same thing here. You use a variety of approaches to try to solve the problem.
You mentioned dimensionality. I'm just wondering if there's some sort of upper end dimensionality.
But by dimensionality, do you mean data size or model size? So Bayesian methods scale very well with a model. So if you can have lots and lots of parameters, you know, I've seen like forest fire models where every tree in the forest has its own parameter. No problem. It doesn't scale well with data with n, right? Because, you know, every iteration, see what has to happen. It has to have that accept, reject step. Problem comes in. That's where things like mini batch can improve on that, or at least make it faster. But sorry, upper end, if it's a simple model, like you can have a 100-dimensional multivariate normal, that's a hierarchical model with multiple hierarchical levels, depends on kind of the structure.
Quick question, how can we get in touch with you after the presentation?
Well, you can email me or come, well, if it's about PyMC, the best place to go is to our discourse page. And I'm on there, the rest of our developers are there, it's a pretty good community. So if you're trying to solve a particular problem, that's the best place to go. But in terms of getting in touch with me, yeah, I'm on Twitter. My last name is my handle, and my email address is Gmail with my last name is my account. So I have an unusual last name, so I usually get Fonnesbeck for all of my users.
All right. Oh, go ahead.
Real quick,
Last question,
Can
okay.
you do a graphical model
Like,
graph?
yeah, like a Bayes net sort of thing.
Not a neural network type thing.
No.
But, you know, a decision.
Yeah. And it isn't optimized for that sort of thing. But you can construct them using the components of PyMC. We've had sort of proposals from various people for kind of adding a specific submodule for doing Bayesian networks, but we haven't done that yet. So you can do them, but it would involve a lot of manual kind of legwork. Again, it's a very general package, so you can do a lot of things. What we're doing now is kind of accumulating specialized pieces that allow you to do them easier. Like GPs used to be, you were able to do them in PyMC2, but you had to do them by hand. And now you can just say you're a GP in one line, essentially. I've got a graduate student who's working on survival models in PyMC and having classes for survival models, so that will knock that out. So we're hoping, and if you have expertise in this stuff, yeah, so there's an opportunity for getting a better job done with those. Okay, that was 4 questions.
Yeah, so if you have more questions, please feel free to stay to talk with us and hang out tonight. And also, we want to shout out to our sponsors, Axel Healthcare and NTC, for providing us the venue and refreshments. And you might have noticed that Jason, one of our organizers, have been recording online. And so we'll put out the recordings on our YouTube channel, which I'll post to our Meetup page. You can just find out the link. This event has also been live streamed, so if you wanted to, learn more about the GP or like go back to the presentation in a bit more detail, you can check out our YouTube channel. So thank you all for coming, and thanks again,
Thanks.
for this engaging tour.
Thank you. Yeah, good.
Yeah. I'm really, I'm a big fan.
Oh, good. Wow.
I'm not, like, very strong technical